子谦有来吗？没有来，还没有来，怎么还没有来？哪一个 project？这个 project？哦，诶，跟他讲一下他的那个，他 send 给我那个 zip file 恐怕不到，还有东西没有 send 到给我，我发他没有回我。Okay, so since today is the last day, we won't have proof today. Okay, never mind. So we'll set some more uh, object that which we're not gonna use, but I think it's useful to talk about them so that in future you will go deeper into algebraic geometry, you will see them again. Okay, yeah. So they are very um, contemporary item to be used. Okay, so yesterday we stopped at this Riemann-Roch theorem here, stating that if C is a projective curve of genus G, so yesterday we defined this genus G as a number of linearly independent um, vectors inside where inside the vector space. So what vector space we are consider here? Actually, these are all the effective divisor that are linearly equivalent to a canonical divisor. Okay, so effective divisor says that all your coefficient of your divisor have to be greater or equal to 0. Okay, and then how do we define canonical divisor yesterday? Anyone remember or not? How do we define canonical divisor? What's canonical about this divisor? Sorry, guys? Something about one form. Yes, something about one form. So this canonical comes from another vector space, right? So what is the vector space that we consider yesterday? The omega 1, right? Okay, so if you learn differential manifold before, so this omega 1 actually is the one form that defined on the curve. So omega 1 here is what? How do we define omega 1 here in our class? So how do we define this omega 1? Let me see. So it's an equivalent class. So you could imagine that this equivalent class is introduced on the open set. So what does this open set to do with the one form here, which we call a differential form? Okay, so basically it's something that can be written as a linear combination of T GI here, where the coefficient live in the order. So these Fi are regular parts. Okay, so this DGI here is not the it's not exactly okay the differential is the differential form, but last time we defined this using an algebraic way using this. Okay, so if we want to define what's a df here, we just take f minus fx mod mx squared. Okay, so this is the algebraic version of differential form. Okay, we discussed yesterday that this definition kind of makes sense because if you take away fx, right, it's like you take away the constant part. Okay, take away the constant part. But like in the calculus differential, right, you also, after you differentiate, the constant will disappear. Okay? And then the rest will take care by this mx squared. Okay, and then yesterday we proved that the gamma 1 of a curve is one dimensional. Okay, so we just pick out the basis here. to what we call as a canonical divisor. Okay, so this canonical divisor here have some role here. So if you compute little d, little l on d, and take away the little l on k minus d here, what you obtain is a topological property here, okay, which is 1 plus d minus g. Okay, so on one side, you are taking a difference between the dimension of vector space. On the other side, you have some genus and degree of divisor combination. Okay, but this G here actually is we define as little L of K. Okay, a little L of K. So if you like, you can put all the little L on one side, and then on the other side, it just has 1 plus D. So D plus 1. Okay, so there are few useful corollary here. So one corollary is the canonical divisor has an even degree, okay, which is 2G minus 2. So if you learn maths enough, I think 2G minus 2 is a very familiar figure for you. Where have you seen 2G minus 2? Anyone familiar with 2G minus 2 here? Maybe something about Euler characteristic. No. Then meaning you don't learn enough. Go back and learn again. Okay, so something on the Euler characteristic. So maybe next time we will gonna see 2G. Okay, and then next is Riemann's theorem. So if D is a divisor that is greater than 2G minus 2, meaning you are larger with degree larger than of canonical divisor, then we can straight away compute the little L of D, okay, which is D plus 1 minus G. Okay, basically you force the degree of K minus D to be negative, and then we yesterday we proved that if your divisor have a degree negative, then L of K minus D is a zero space. Okay, before we finish up the whole semester lecture here, I want to talk about this projective embeddings here. So basically, if you have a function, okay, from x to y, okay, sending p to q, then on pullback, right, on pullback on the function view or polynomial ring, depends on what kind of morphism you look at, then we can pull back on this maximal ideal, okay, on q and p. Okay, then you will induce a map on the quotient, but then by duality, right? If you consider the star of it, so this is the four tangent space, right? So if you put a star on it, then you will have an isometric to the tangent space, which we call the df. Right. So why do I say this? Because if a morphism from x to p and k of a projective variety here, so you map a projective variety into a projective space, it's called projective embedding. Okay. If f is injective and the differential is injective at every point. So what does this mean, sir? This means that this object here, right, put inside this space is injective. If you look around the tangent space around it now, feel injective into the tangent space of this space here. Okay, not just this object itself is injective, but the tangent space of this object is also injective inside the project. Okay, so kind of special here. Right, I think this is one of the definition you will see when you start learning differential. Yeah, differential geometry or differential manifold. It's embedding submersion right？什么？这我没有教啊？没有教呗？那不课本的第几个？第几千几页吧？喂？什么？ 把它删掉了。OK，问题好像怨气很重的，把它删掉。OK，把它捡回来，捡回来。Okay, okay. So next proposition is if X is a projective variety, right, and Fx to Pn is a projective embedding. Actually, what can you see is the image is actually a sub variety of Pnk, and F induces an isomorphism, okay, from X to its image. But this, I thought this is what we introduce an embedding in general topology, right? Do you remember? In general topology, we introduce embedding as it is because there's only topology thing you can describe there, right? So we talk about injection, and then we talk about homeomorphism, right? Homeomorphic to the image. But the result of the injective tangent map result the similar idea of embedding of topological space. And when we force the tangent space to inject into the tangent space of the whole space, then actually you are inducing an isomorphism. Okay. You see, isomorphism have to come after fx to be sub, right? Yeah, because we need to talk about isomorphism of variety here. Okay. So here is a Zariski topology. Okay, this is the Zariski topology. In the general topology case, the homeomorphism, right, is a random topology. Okay, here is a Zariski topology. Okay. So there's no proof here since I already said Hudson is I think it's a long proof. Maybe one day the Hudson proof could be easier because you could be that person to make it easier. Actually, I found out that Klaus, because Klaus is an extension of Maurits, right? If you realize there's something extra that Maurits, right, in Klaus. And then I found that some of the proof, right, actually he get from Hudson. Okay, again, he get from Hudson and then he put it as a simpler language. Because Hudson tend to like put them into a language of homology, but Klaus will like try and simplify it. Yeah, so it's possible. Okay, and next, yesterday we defined this already. So just now, not just now. So the divisor D define a complete linear system. Okay, so yesterday we mentioned about this. So basically, we are like collecting all the linear equivalent effective divisor. Because yesterday we proved that if D prime linearly equivalent to D, their LD will be isomorphic. Okay, the vector space that defined by this divisor will be isomorphic. So we are collecting all of them in this homologous D here. This one we mentioned already yesterday, and then we show that this complete linear system actually is a projectivized LD. Okay, actually is a projectivized LD. So it's not hard to think about this projectivization because if you have a divisor, right, you multiply by any unit here, you're gonna define the same divisor because unit doesn't contribute to zero poles, extra zero or extra poles. Okay, it won't change the multiplicity anymore. And so the whole line will define the same divisor. And then we talk about base point yesterday. Do I go through again? Maybe talk in the middle. We go through a base point. So what is the base point? Base point meaning even if you take away the base point, right, and you go and intersect with the original linear system, you're gonna get back your linear system. But if once you take away a base point, it's no longer your original linear system after you doing the section, then you will say base point free. Okay. Okay. These are for the sake of talking about amber stuff later. Okay. So I think is this the final thing we're gonna do? Okay. I think the final goal we want to achieve is we want to ask whether what divisor will give rise to embedding. Okay, what kind of device will give rise to embedding? So maybe you want to ask, oh, Then give me a divisor, how I produce a map. Okay, so here is how we produce the map. So if I give you a divisor, then you can consider a modulus of D. It's also a base point free complete linear system here. Okay, so these are all the effective divisor that are equivalence to D, linear equivalence to D. Okay, and then the map 5D is called the map defined by the complete linear system. It's defined as follow. Okay, so let L be the LD, so the dimension of capital LD, right, greater than 0. Then what we do is we just pick bases from here because it's a vector space, right? Then actually this will define a map from C, the curve C that we have the divisor on to the projective space, okay, of PL minus 1. So let me show you one example. Okay, let me show you one example here. So let's say we start with a P1 here. Okay, so P1, the homogeneous coordinate is x1, s not s1, okay, because you use A2 to build your P1. Then let's consider this divisor here, 3 times infinity. Okay, meaning what? It has a multiplicity 3 at infinity, okay, as a 0. So infinity here is 1, 0. Okay, we fix 1, 0 as the infinity point. Then, what is LD here? Okay, you can try and figure out what is LD here. So we compute here. So yesterday I didn't really show you some concrete example, right? So here we show you the example. What is LD here? So I mean like let me see here. Yeah. Okay. So if I have that D, right, it says that it has a multiplicity 3, okay, of 0 at infinity, at 1, 0. So what point take 1, 0 as 0? Huh? What point take 1, 0? X1, right? Okay, X1. But now you got multiplicity 3, so S1 cubed. Okay. Yesterday we talked about this LD, right? LD is what? It's the thing that you add to S1 cube that is greater or equal to 0. Okay. That's greater or equal to 0. So naturally, you will think of these 4 elements here. Naturally, you will think of these 4 elements here because this one has negative 3, right? Negative 3 plus 3 is greater or equal to 3. Okay, on that. So, okay. So naturally, you will think of this examples here, this vector space here. Okay, this vector here. Should we have more? Should we have more or not? Should we have more? What do you think? Should we have more? Think. Could we have x naught to the power 4 over x1 cube? Why there's only 4 things here? Try and think about it. Why there's a 4 things? We have x naught to the cube. Huh? Maybe recall what is LD again. So what is LD again? So LD are all the F such that F plus D is greater or equal to 0. Okay, so what's our D here? Our D here is supposedly x1 to the cube, right? Wait, so no, I can also write like this. So how do I write it? So let's say D is equals to, sorry, D is equals to some principal divisor. Then maybe F look like this. So my question is, what happened if you consider, let's say, like x to the x naught to the 4 over x one cube? Shouldn't be, right? We cannot have this, right? Why? Because this 2 is not an element of, this is not an element of KC, right? Because this is in a homogeneous, this is a projective variety, right? So the top total degree should be equal to the bottom total degree. Okay, so let's say we do another stupid thing. Can we do stupid thing or not? Can we do something like this? Oh, so next level is increasing already. Is it? Is it increasing? Maybe not increasing. Oh, so how about, let's see, let's think again. So let's say we go to this level. What could happen? Is it living in LD or not? So this one increased already, right? So that one should be decreased. So not good also, right? Okay, so how about, let's say go to this level. Put in LD. But this is what we consider, right? Okay. So if you go higher power, what happens? Then you will not live in LD anymore. But if you go lower level, this is all the thing that we consider here. Make sense? Does it make sense? Did you notice that all these basis element, top and bottom is the same homogeneous degree? Because this is the function that we can define on projective, right? Still remember the LD on the top and the bottom, we need to pull the same number of factor up to be well defined. Okay, so you see, so in this case here, this map, this embedding map here defined by a linear system here really give you an embedding there. If you still remember in a week, I think week 6 or week 7, actually you see this curve before. Sorry? SEGI, Segre embedding. Uh, is it that? But I'm not talking about that. Is it that? That one is for product, right? The product of PN here. This one is this cubic normal map, cubic normal curve here. Okay. I think last time I asked you to like figure out what's the equation that defines this curve, right? If you remember. You remember or not? I give you this coordinate map and then I ask you to think about what function define it. And then when Chan asks, how do you know there's only one is enough to define this function? Something like that. Okay. So you see, from this construction here, we produce a variety, okay, an embedding of a variety. Okay, from this linear system stuff. Okay, this LD stuff, this divisor stuff. Okay, we can produce another variety. Okay, and then we can talk about more about this condition. So a divisor D on the curve is called very ample. Okay, if this modulus D here is a base point free. Okay, so the complete linear system is base point free. Moreover, this map here that we construct here is an embedding. Then we will call this divisor very ample. Make sense? Okay, so these two joined together, we will call this divisor to be very ample. Okay, for if it was for the special case that we consider in this class, right? So we consider curve, right? These divisor actually are called line bundle. And so if you read the literature, okay, whatever we define here is a line bump. Okay, because due to the low dimensional variety that we consider here. And then you can prove that these two are equivalent. So D is very ample if and only if for any 2-point dimension of D minus P minus Q equals to dimension of the complete linear system minus 2. Okay, so you can use dimension of D to check whether this D is very ample. I think both of these are quite hard, right? So one of them you need to check is base point free and then check embedding. The other one, although you need to check for all points, but really you just need to count dimension. Okay. So relatively easier, I would say. Okay. Both are hard also, but yeah. Then proposition is if your C is a smooth projective curve of genus G, okay, and D is a divisor of degree D, then if you know the relation between the degree and the genus, so if D greater or equals to 2G, then D must be base point free. If D is greater or equal to 2G plus 1, then the linear system must be very ample. Okay. D is very ample, or I think it's D is very ample. Let me see. I think it's D is very ample, not the modulus D, because ample defined on the divisor, and then base point free could be defined on linear system. Okay, finally, then you can show that if F is a non-constant morphism between two projective curves, if you know that the codomain is smooth, then F is surjective. I think in tutorial also have this kind of surjective property, right? Did we? Oh no. Maybe no. Maybe I think of the wrong stuff. But I remember I asked you to put something on surjectivity. Did I? In tutorial? Some finite fiber stuff. Okay. So let me see. Yeah, okay. So if your curve is genus G greater than or equal to 2, then your canonical divisor will define a base point free linear system. Okay. And a smooth curve is called hyperelliptic. Okay, elliptic, hyperelliptic. If the genus is greater than or equal to 2, and if there is a surjective morphism to P1 of degree 2. Then the proposition here is if your curve is genus G greater than or equal to 2, then either the canonical divisor defining the defining what? Defining the complete linear system is very ample, or actually C is hyperelliptic. Okay, so there are only this is like a classification on what could happen with a degree genus 2 quadratic curve. Okay, then if K is variable, then the embedding, okay, defined by this complete linear system here is what we call the canonical embedding. Okay, and then this image will be called the canonical model. Okay, in this kind of model, right, it's kind of how to say, it's a natural problem that algebraic geometry will think about. Okay, so like for example, what? For example, the resolution of singularity, right? So people will ask, so So when you resolve it, so what's the minimal smooth projective? I mean smooth variety. Okay, that you can do the resolution. Okay, and I think there's something called the minimal model program as well, but I forget what's minimal about that. I think it's a projective stuff, if I'm not wrong. For example, right, like the circular embedding, right? So we also embed into some projective space. And but why is it that space? Can we like make it smaller or not? Or what? Yeah. So this kind of modeling question is kind of same in algebraic geometry. Okay, any questions so far? I think this is the last slide I prepared. Half an hour. Jury to lunch can finish already. No lah. Any question? Finish already, this one. Finish. 763 slides for this 15 weeks. Yeah. Yeah, sure. Yeah. 我已经 like 没有空找，先放在那边吧，以后再说。可以把它转换一下吗？就是转换成我们的 symbol，我只是来没有空去来一个去，yeah，转换成我们的符号，yeah。Any questions so far? Oh, yeah, I will. About average 50 slide per week. So we got 2 days, about 25 slide per day. Obviously, sometimes fast, sometimes slower. Okay, but this is like how your body react, right? Sometimes fast, sometimes. Right. Sometimes I have to work hard, sometimes take the rest. Okay. Any question? Yes. I think so. Yeah, definitely. Yeah, definitely. Yeah, definitely. Yeah, so the discussion about the divisor here, right, could be replaced with higher dimensional. Like what I said last time, right? So the divisor we consider here are just core dimension one actually. Okay, so you can consider different core dimension. So the core dimension one will define what they call a Picard group. I mean for the class divisor group. But if you consider different core dimension, I think that's what they call the child group. Yeah. Yes. Yeah. Hopefully in one day, we can touch all these. Actually, I'm quite interested. That one, I think we need further abstraction. Because if we go to higher dimension, rarely you can draw the variety of. It's rarely you can draw the. It's similar case for differential geometry. It's really just maybe vector calculus 2, you can draw it out. But if you go to higher dimensional, it's a Riemann geometry. Right? How do you draw it? I don't know. I don't know how to do it. At least I don't know. Okay. So yeah. So if you think that this part is already very hard, so I will encourage you to think even harder question. Then you will make this less hard. That's how I approach stuff. Okay. If you think that your life is very bad, go and look for another life that's worse than you. Then you will be more grateful already. Okay. But nowadays different, When you go, maybe you go to Bukit Bintang, right? You all know Bukit Bintang, right? Okay, if you are from here. Maybe the beggar have a better life than you. They could earn more than a professor earn in one day. Life is changing, you know. Okay. Any other thing you want to ask? Yes. Other types, you mean like you mean this proposition here? Are you referring to this proposition? Oh, hey, that one I'm not sure. I'm not sure how this hyperelliptic get linked to elliptic curve. I'm not sure they are related or not. Yeah, I'm not sure actually. I'm not sure. Hmm. Anyone know any elliptical expert here? Yeah, I don't know. No idea. No idea. No idea. I actually first time see this thing when I prepared. Yeah, just find it fun that we can put this discussion with very Apple devices. Any other question you can ask out of like learning after learning course, yeah? Or based on what you have learned, can you like connect them? Definitely, people are connecting them at the front already. But those are quite abstract. Yeah, so sometimes the language in this class will go wild because there's a different level of students here. So I should like cater cater you. Yeah, although I mentioned that we might skip some of the chapter, but it seems that we did cover a little bit of intersection theory. We also cover a little bit of device selection. Yeah, although we don't go in deep to the technical tools or what, but we did cover the concept. Okay. But for the project, I already signed you in. You can do your turn it in check. Okay, signed you in. So don't abuse it because after 3 times, you're going to wait 1 day for the report. So after you get a report, please do the correction properly so that it don't generate you a plagiarism rate again. Okay, because after 3 times, you're going to wait. And don't do it the last day. I cannot force the robot to work for you. Uh, there's a rule there. Anything? Should we discuss tutorial today? I mean, not assignment. I mean, 3 and 4 I haven't discussed with you. I'm almost finished marking assignment 3. Hopefully tomorrow I can give you that. And then I will mark assignment 4. And then I'll wait for your project. And then your final assignment. Okay. So final assignment, there's no extension. You want to do it as a take-home exam also can. So if you cannot finish, but you have to submit also. Okay. And then anything else? Anything else? So okay, so revision was scheduled at Thursday, or 1 day after your submission. All right. So there's some of you are in general topology, but not in general topology, but in this class, right? So we got a FYP recruitment on the next Friday, so which is after general topology revision. So it's 4 to 5. So 2 to 4 is revision class, 4 to 5 briefing. Okay, but I also actually put out the thesis by my student actually on the Moodle, so you can have a look what kind of flavor they did, and then what sort of thing they did. So my plan is to maybe go beyond that or using that, and or you have some interest around those topic, then we can do it. Okay. So are you guys free or not? Siyu and Sayed. Not free. Next Friday. Got class 咩？什么？你回家啊？你回到几时？啊？你下个礼拜没有考试？你 revision week 没有考试？你没有考试？哦，因为OK。思雨耶你可以。没有，我其实要 meeting 了，来，我们要 meet 一次，应该最后一次了，因为金宝是11号才回来，所以你几时回去？谁？啊？拜几？什么？这个星期五？哇，你很享受给你妈宝回去了。这样的话，不是要等你回来，要 meet 什么？很直接，你要 meet 什么？就是 FYP 最后一次 meeting 哦，祝你们好运。没有了呀，这样就等你回来啊，应该要等你回来吧？那个谁是11号回来我？那11号是拜几啊？拜五啊？我拜五没有空，哦，我也没不到。说你回到21号啊是吧？你回到20号，是不是你们要准备考试哦？还是再看呢？看要在考试前还是考试后？maybe 考试前会比较好，maybe 21、22、23的，看一下你们的 schedule 怎样，在群里面再问等金宝回来。你们有留下来读 master 吗？没有，你没有读，你去哪里？你回家啊？什么？休息一下啊？OK OK，休息。你是回去做工还是什么？什么？回去做工？对，没问题。嗯，好想现在。Yeah, do you want to discuss assignment today or not? Or you want to do whatever you like? You can do whatever you like, but that's your choice. Then we can call it off a day. 好了，you want to discuss assignment or you want to yes? Sorry, you want to go home? What did you say? You want to go home? Huh? You want to go home? You can go home. But I mean, how about the rest? You want to go home? You want to go home? I mean, if we don't discuss, then we can leave to the revision day to discuss. How about others? What do you think? It's okay one. It's okay. You already grow up. You need to make your own decision. Need duration. Sure, sure, good. Yeah, makes sense. I think this is a very good reason. We just need to find a reason, right? Okay, in that case, how about we take a group photo and then we call it a day? Okay, let's take a group photo. Maybe here, here. Maybe take it here. 哪一个？just OK OK，可以。Can. So let's take a photo and then I will find it. 来，我们拍个照，我们就结束了。 不然比较好一点。那让您帮我们拍照对吗 ？Right？ exam over. Yeah, so exam is one double-sided A4 handwritten. Handwritten. If you print it out, then exam unit don't accept, you can throw it away. Because it's checked by exam unit, not me anymore. It's not like midterm. Midterm 我还可以给你们一些那个通融。
别人写完
的
复印边上，
啊，
别人写完了复印边上。
我都跟你讲，不能够是印出来了，是太 return。
那我就直接就是。
Yeah. Let's take a photo together. 来。Then you can do whatever you like.
是哦。
Quick. 这个清楚点。高的在前面，更高的在后面。看到吗？拍一个画面，随便拍吧，我可以理解。
OK，随便摆一个，我看你，我就看你，我装的，要不要一个直？直的给他发 story。
对吧？对吧？Okay, so thank you. Thank you for the semester. You learn a lot.
学期开学之前给你。
好。